Okay, I think it's time to start our next talk by Etienne Marion from ENS in Lyon. I will talk about the probability theory, a bit of formalization of the Ionescu-Tulcea theorem in Mathlib.
Okay, so hi everyone. Thanks for the opportunity to talk here. So I'm going to present formalization of the Ionescu-Tulcea theorem. This is work that I did during an internship supervised by Sébastien. So it was in mid-2024, and most of the cleanup and upstream to Mathlib happened in early 2025, so nearly a year ago. So I'm first going to talk about the mathematical statement in itself, and then I'll present some aspects of the formalization that I find interesting. So this is a probability theory theorem. So I'm just going to assume that you know what a measure is, but otherwise I'm going to define what Markov canals are, because they are the central object of the theorem. And then I'll also give a quick sketch of the proof. So Markov kernels, I'm taking two measurable spaces x and y, and a Markov kernel from x to y is a measurable map from x to the set of probability measures over y. So you need to put a sigma algebra on this set. I'm not getting into details here because the measurability actually does not cause any issues in the formalization, so I'm basically not going to talk about it. But what you should remember is that it's kind of like a map from x to y, but with a random output, because the output will actually follow the distribution that is the output of kappa. So throughout the talk, what I'm going to say is that if I have a kernel from x to y, I'm going to denote it with this squiggly arrow. And if I have a point in x, then I will write kappa of x as a point of y, but I'm thinking of kappa of x as something random. And so I'm putting quote here because this is not formally right, but it's a good intuition. And so with Markov kernels, there are many different operations that we can do on them. So I'm going to present the ones that I'm going to need. So first we have the push forward. So if I have a kernel from x to y and a function from y to z, then I can define a kernel from x to z. And to do so, I just start by applying kappa to my input x, and then I get a random point in y, and I can apply the map f to get a random point in z. I can also take the product of two kernels. If I have a kernel from x to y and one from x to z, then I get a kernel from x to y times z, and I just put kappa on the left and eta on the right. Kernels are also, as I said, they are kind of like random maps, and so you can also take the composition. So if I have a kernel from x to y and a kernel from y to z, I can take the composition of eta and kappa. From x to z, I first get a random point in y, and then I can apply eta to that. I get a random point in z. And the last operation, which is maybe a bit more complicated, is what we call the composition product. At least that's what we call it in Mathlib. So we have a kernel from x to y and another kernel from x times y to z. And the output is a kernel from x to y times z. And to do that, what we do is that first we need a point in y. So for that, we can just use kappa. And then we need a point in z. And to do that, we can apply eta. And to apply eta, we need a point in x, which is just our input, and a point in y, which is just kappa. So what's happening here is that we first apply kappa to get a random point in y. And then thanks to that, we can also apply eta to get our second random point. Okay, now that we have that, I'm going to present the setup of the theorem. So I have a family of measurable spaces which are indexed by natural integers. And for each n, I have a Markov kernel, kappa n, from x0 times xn up to xn plus 1. And the idea is that kappa n takes as input a sequence of points which you can think as some kind of partial trajectory, and will output the next position of the trajectory, which will be the space xn plus 1, and so which will be a random trajectory. So I start with an initial point x0, then I can apply kappa 0 to get a random point in x1, then I can apply kappa 1 to my trajectory x0, x1 to get a random point in x2, then I can apply kappa 2 to my partial trajectory to get a random point in x3, and so on and so forth. And so by iterating my kernels that way, I'm building a random process where each position is determined by the kernel kappa n, provided the past trajectory. And so what I'm basically doing here is that the sequence I'm building is just what I get when I start with x0, and then I apply all my kernels, which I take the iterated composition of all my kernels, and so my kernel has this type, and I get my partial trajectory of my process. And a natural question that arises there is whether we can do this process infinitely many times, in the sense that there is a kernel which outputs not only a partial trajectory, but an infinite trajectory directly, and which is in some sense the limit of these kernels there, these partial kernels that I have there. So it's quite natural, and fortunately it is indeed true, although it's not straightforward. And this is exactly the content of Ionescu-Tulcea theorem. So for an integer n, I'm going to denote pi n, the projection over the first coordinates, so canonical projection. And what the theorem states is that there exists a unique Markov kernel xi, which outputs an infinite trajectory, such that for each integer n, if you take the projection of xi on the first coordinates, you find the partial kernel that I was talking about just before. So it is in that sense that xi is some limit of those kernels. And this equation here completely characterizes xi because we have a uniqueness in the theorem. So there are a few consequences from this theorem that are quite nice. So for instance, if we take all the spaces to be equal to a certain space x, and all the kernels to be equal to a certain kernel kappa, which is from x to x, what I mean here is that kappa, instead of taking as input the whole past trajectory, actually only takes as input the very last position of the trajectory. So it forgets about everything that was before, it only remembers the last position. So it's the process that we're building is actually a process without memory. And this is what we call a Markov chain usually. And so the kernel psi that the theorem gives is actually the Markov chain with transition kernel kappa. So this theorem gives the existence of Markov chains, discrete time Markov chains, without any hypothesis on the state space. So that's kind of nice. And another interesting consequence is when all the kernels are constant. So a kernel is a map which outputs a measure, but if the measure is always the same, you can basically consider your kernel to be a basic measure. In that case, this composition product becomes the product measure. And so your kernel is actually also a measure, such that when you take the projection, you get the finite product measure. And so xi will actually be the infinite product measure of all your probability measures. So the theorem gives you the existence of the countable products of probability measures. And once you have countable products, it's not hard to also get uncountable products. So that's some part that I also formalized along the way, thanks to the theorem. This theorem is also quite useful in stochastic algorithms. So it's not a field that I'm familiar with, but I know that it's quite useful there. And a few remarks I want to make is that this theorem was already formalized in Isabelle in 2017, so it was some time ago. Although in Isabelle, there aren't any dependent types, so all the xn's are actually the same. And if you want some mathematical reference, you can check Kallenberg's book, where there is the general proof of the theorem. And I also mentioned Kohn's book because there's only the proof for the product measure, but the key argument is still there, and there are much more details in Kohn's book, so I think it's easier to follow. And now I'm going to give a quick sketch of the proof. So basically, we want to build a kernel. So given an input, we want to build a measure. And to build the measure, we will first build it over sets which are easy, and then we try to extend what we already have. So the sets which are nice are what we call measurable cylinders, and those are sets that only depend on first coordinates in the following sense. At the beginning, they can be anything as long as it's measurable, but starting at certain rank, they have to be equal to the whole space. What is nice about these sets is that we know what measure they must have, because our theorem says that the kernel we're building must be equal to a certain kernel when we restrict to the first coordinates. So actually, this cylinder must have this value under the measure we're building. So what we do is that we define this map P0 with x0 being the input of the kernel. We define it over cylinders in that way. And it's an additive content because it means that it maps disjoint cylinders to the sum of their measures. And we just want to show that this content can be extended into a measure over the whole product sigma algebra. And to do that, we use Carat-Theodory's extension theorem. And the key lemma to do this is to show that if I have a non-increasing sequence of measurable cylinders with empty intersection, then their content tends to 0. So this would be obvious if this was already a measure, but we want to show that it can be extended into a measure. And so we actually need to show that. And so a brief few words about the proof of the lemma. I'm not going to give all the details, but we use sections of sets. So if I have a subset of the product space, I can take its section with respect to x1, xn. These are the elements of the product starting at n, such that if I put x1, xn at the beginning, I fall back into A. So it's almost the elements of A that starts with x1, xn. And what we do in the proof is that our cylinder can be written that way, because it only depends on first coordinates. And then its content is defined like this. And so we can use the definition of the composition product to write this as an integral. And so here we have a new x1 which appears and which appears there in the kernel, and we have to use the section of Bn. And we can iterate this computation with x2. So we have x1, x2 there and a section. And we actually do this over and over again. And then we do a reasoning by contrapositive. We assume that this quantity is lower bounded. And so we can find x1 and x2 such that this quantity we are integrating is actually also upper bounded for a certain x1 and x2. And I'm not getting into details, but we can do that independently of n. And we can do that to find an x3 and an x4. And we are building a sequence which will belong to the intersection of an, contradicting the fact that their intersection is empty. The reason I'm showing you this is that this idea of using sections of sets and iterating integrals that way is not easy to formalize. So it's something that I will talk about later when I talk about the formalization, which is right now. So first I want to talk about what was already available, because when we started, because there was quite some stuff already. In Mathlib, Markov kernels were already there and all the operations were already defined. So this has been mostly done by Remy, and there's a nice paper from a few months ago which describes how Markov kernels and how kernels are used throughout Mathlib, so you can check that out. And also in Kolmogorov extension 4, which is a GitHub repository from Remy and Peter, they formalized Kolmogorov extension theorem, which is very similar to Ionescu-Tulcea because it's the same proof strategy, basically. And so in that project, they had already formalized Carat-Theodory's extension theorem, cylinders, additive contents, and projective families of measures, which are also relevant. So we added a bit of API to those notions, but there was already most of it was already done, so that gave us a huge head start. So now I'm going to talk about what was not available. The main challenge of this formalization is the composition of kernels. So the composition product was already defined, but we actually need to take an iterated composition. And this is not easy because composition product is not an associative operation. So you can see this, if I have 3 kernels, kappa from x to y, eta from x times y to z, and xi from x times y times z to t, well, I can take the composition of kappa and eta in that way. And then if I want to take the composition with xi, I need to put parentheses here to make sense. And because y and z are together, I need to put parentheses around y and z. And so I get this composition. And now I want to compare this with this other kernel with another parenthesis. But this does not make sense, actually, because you can't take the composition of eta with xi because their types don't match. So you actually need a xi prime with different parentheses, which is the same as xi up to some isomorphism. Then you can take that composition, and the 2 kernels that we get at the end do not have the same type. So we need another isomorphism to compare those kernels. So on paper, this is not an issue, but in Lean, it can quickly get unusable if we have too much isomorphisms. And we have even more issues with that because if I take A and B two integers, and I consider this kernel. So I assume that I'm able to define this kernel. And I'm also assuming that I can define this kernel here. So this is takes as input an element in x0 and outputs a trajectory which is indexed by integers between 1 and a. And this one takes an input which is a trajectory up to time a and outputs a trajectory between times a plus 1 and b. And if I want to take that composition, I want this to give me a kernel that outputs a trajectory from times 1 to b. But to do that, well, first I need that to show that, I need to say that this type is actually the same as this product type there for the composition to make sense. And then the output that I will get has this type. So I need another isomorphism to get the output type that I want. So even if we manage to define this composition, we still can't compose them together. So there's a real issue here, and we didn't manage to shake off isomorphisms while attacking the problem this way. So we took another approach, which is the following one. So what we did is that we define eta for a and b integers. We define eta ab, which are kernels, which is a kernel which take as input the trajectory up to time a and outputs the trajectory up to time b. So it's not the trajectory between times a plus 1 and b as we had before. It's the trajectory, all the trajectory up to time b. So it's defined in the following way. I have my input. If b is smaller than a, well, then the trajectory up to time b, I already know it. It's just given by the input. And otherwise, the first steps are given by the input, and then I can do my iterated composition there. And the way to define this in Lean in a formal way is to introduce these isomorphisms. So I have one isomorphism that states that xb plus 1 is the same as the product of xk when k is only equal to b plus 1. And this says that integers smaller than m plus integers between m and n gives me integers smaller than n. So these are obvious maps. And then I can make this definition. So it's an inductive definition. If I know that eta ab, I defined it, I can define eta ab plus 1 as well. So I'm not going into detail as to why this expression makes sense. You can try to check it out with the definitions that I gave at the beginning of the talk. But the nice thing about this definition eta is that if I have a smaller than b smaller than c, then I can write this equation there, which is quite natural actually. So if I have the trajectory up to time a as the input, this gives me the trajectory up to time c. This gives me the trajectory up to time b, and so I can plug that into this to get the trajectory up to time c. So those two objects should be equal, and they are actually equal. But the nice thing is that this time this computation makes sense without any isomorphisms. That's something that you can write in plain Lean without any issues of isomorphisms. So that's what we did. So partial traj is just the name that I gave to eta. It stands for partial trajectory. And you can see that we indeed have eta AB composed with eta BC gives eta AC. And the proof is actually quite easy because of the way eta is defined inductively. Another nice property that we have with these kernels eta is that if I have b smaller than c, I can look at eta AC and I can restrict it to coordinates which are smaller than b. That's what the map pi here is doing by CB. And if I do that, I get eta AB. So I have this family of kernels which are nicely defined and they interact with each other well and with proper operation which does not need any isomorphism. So we can use all the API that we have for Markov kernels in Mathlib. So that's quite nice. The second point that I wanted to talk about was what I call peeling off integrals. So that's what I talked a bit about in the proof sketch. So basically, I wrote this computation in the proof. And the issue with that is that mainly comes from these sections of sets and also the fact that we iterate integrals. So Bn is a set from a certain product space, but Bn of x1 is a set from a product space with a different index type. So this is indexed by integers, and this is indexed by integers greater than 1. Then you iterate, you get integers greater than 2, and so on and so forth. So you've got a lot of different subtypes going on, and you're getting close to what we call a subtype hell. But fortunately, very early in the project, Sébastien suggested that I look at something in Mathlib that's called L marginal. So it's an idea from Floris Van Dorn and Heather Macbeth. You can check their paper from 2024. And it's the idea is the following one. if I have a family of measure spaces, so mu I here is a measure, and I have a function defined over the whole product space and a subset S of coordinates, I can integrate F against the product measure there. And to do so, I can first integrate against coordinates which are inside S, and then coordinates which are not in S. But writing this equality does not make sense in Lean, because here my function takes as input an element of this product space, while here it takes as input two different elements from two different product space. So in Lean, you would need to add an isomorphism somewhere for this to make sense. And so the issue is that when you integrate against the coordinates which are in S, you actually consider this as a function which only depends on the coordinates in the complement of S, so you only integrate on this space there. And so what Floris and Heather said was that no, actually, this inner integral, we're going to call it L marginal mu SF, and it's a function which is in fact defined over the whole product space. But so when we take X as the input, inside the integral, we replace the coordinates of X, which are indexed by S, by those that we get from the integration. So in practice, this quantity only depends on the coordinates which are not in S, but it still requires the input of the whole product space. And this makes things much nicer because all your integrals are over the same domain and you don't have any issues anymore. So I really like this trick because on paper math, it doesn't really make sense, but it's very nice formalization trick that really solves the issue. And so we took inspiration from that to define our own version of L marginal. So if I have two integers a and b and a function defined over the whole product space and a sequence in the product space, we defined L marginal partial traj, which take as input my x there and output the integral over my kernel eta ab. And I put into eta as an initial condition, I put the first steps of x. And inside f, I replace x by the coordinates of y, which is my integration variable. And doing so, I can then write things like that. So I can integrate f between b and c. And then once I have that, I can integrate between a and b. And this, writing this in Lean makes sense. And you actually have the result that if you integrate between b and c and then between a and b, it's the same as integrating between a and c. So again, we have a nice things combine nicely. And so the computation that I wrote at the beginning becomes this. So instead of dealing with the measure directly, we write the measure as the integral of the indicator function against the kernel that we care about. And so we can peel things off. And because eta actually outputs a measure over all the first steps, well, then we don't need to deal with the section of A, of AN. It's plain AN there. And because the first steps of eta are deterministic, we still get the same meaning mathematically, but without all the subtypes issues that we had before. All right. And so with all that, we get to the final object that we got. So we have our kernels eta AB, which are deterministic on the first coordinates, and then we have our iterated composition product. So this is only true if A is less than B. Delta is just the identity kernel. And what we do is that we let B go to infinity to get a kernel psi A, which take as input the trajectory up to time A, and will output the trajectory inside the whole product space, which will be deterministic on the first coordinates, and then will consist of the infinite composition product that we cared about in the statement of the theorem. Of course, we need to check that we got the right kernel. So so this is called a traj in Mathlib, and we have to check that it has the right property. So if you take the projection of psi A over the coordinates which are smaller than B, you get eta AB, which is what we expect. And this is true. This is this lemma here. And again, the proof is actually quite nice. And we have also this nice property that if we take the composition of psi B with eta AB, well, we fall back on psi A, which again is quite a natural statement, which is not hard to prove, thanks to the characterization of psi A, which is given by this equation here. All right, so that's it. Everything I talked about is in the paper I wrote about the formalization. So if you want more details, you can check that out. And to conclude, I just want to speak a bit about how this is useful in other contexts. So about the product measure, I didn't talk a lot about it, but it's already used in many places in Mathlib. So for instance, there's this pull request by Yael, who is working on Erdős-Rényi graphs. And I know that they use the product measure in this pull request. And it's also useful, as I said, in stochastic algorithms. So there's a project by Remy and Paolo where they're using Ionescu-Tulcea in its general form, and they've actually contributed some new definitions related to this. And there are also these two papers that I want to mention, which formalize some results on stochastic algorithms, and which made use of the formalization of the Ionescu-Tulcea theorem. And to conclude, I just want to thank Sébastien, who was my supervisor for this project, who suggested the project and gave precious pieces of advice during the project. I also want to thank Remy, who did most of the review work to get everything into Mathlib. And I want to thank the Mathlib community, because whenever we formalize something in Lean, it's only possible because there's such a great community going on. So thank you for listening to me, and that's it.
Thank you very much, Etienne.